Welcome to Module 4 of Multi-Agent Architect. You shipped a subagent in Module 2. You composed a mini-system in Module 3. Now we get to the part where things start scaling and where most teams stumble. Here's the observation that drives this module. When a multi-agent system fails in production, the cause is almost never the model. It's the shape, the wrong pattern for the problem. 2 agents trying to coordinate when they should have been independent. 5 agents fanned out in parallel when the work has hard sequential dependencies. A single generalist trying to do work that wanted 3 specialists. These are shape failures, and they're invisible if you don't know what shapes exist. So that's what this module gives you. 4 canonical orchestration patterns. The shapes that actually work. When each one is the right answer, when each one is the wrong answer, and how to recognize the difference in your own work. By the end of the hour, you'll be able to look at any problem and tell me in one sentence which of the 4 patterns it wants and why. That's the bar. Let's get into it. Quick check on whether you're in the right room. Card 1. You shipped Module 3. The whole composed thing.
Agent plus qu'il plus ou plus / commande.
Not in theory, running, observable with a transcript. If you didn't ship it, pause this and go back. The pattern conversation only makes sense if you have the substrate. Card 2. You can feel the next ceiling. One mini-system was a great forcing function for learning the primitives. But real problems don't fit cleanly into one agent doing one thing. Real problems want multiple agents coordinating, sometimes in different shapes for different parts of the same problem. You can feel that ceiling without being able to articulate it yet. Card 3.
You're ready to design.
The conversation is no longer about wiring 4 files. It's about which shape fits the problem you're solving. That's a different skill. Wiring is technical. Designing is judgment. We're moving from technical to judgment. If you're past wiring and ready to design, you're in the right room. If wiring still feels new, give yourself another week with Module 3 before this material lands. 3 deliverables from this module. Recognize. By the end of the hour, you'll see the 4 canonical shapes everywhere. In your codebase. In other people's systems. In the product roadmap your boss handed you last Friday. The shapes are universal. Once you know them, you'll spot them.
Pick.
For any problem, you'll be able to choose the right pattern and articulate why the other 3 are wrong for that specific problem. Articulating why the wrong answers are wrong is harder than picking the right one, and it's how you'll know you actually understand the material. Diagram. You'll produce a 1-page architecture spec showing nodes, edges, contracts, and failure handling. Real engineering artifact. Not a sketch on a napkin. Something a teammate could read and either build the system or critique your choices. The diagram is the deliverable. If you can draw it, you can build it. If you can't, you've got more design to do. That's the discipline this module is teaching. Map of the territory. 4 canonical orchestration patterns.
1. Parallel dispatch.
And agents work on independent subtasks simultaneously. The pattern optimizes for speed by parallelism. Total wall clock time becomes the slowest worker, not the sum.
2.
Sequential pipeline. Each agent's output is the next agent's input. The pattern optimizes for quality through stages. Each stage gets a focus job, and the contracts between stages catch failures early. 3.
Supervisor plus spécialiste.
1 orchestrator routes to N domain experts. The pattern optimizes for quality through specialization. Each specialist has deep expertise in one area. The supervisor's job is just to pick the right one.
4.
Iterative refinement. Generator and critic in a loop until convergence. The pattern optimizes for quality through iteration when the answer is hard to hit on the first try, but easier to evaluate. Each pattern earns its place by what it optimizes.
Speed.
Stage quality. Specialization. Convergence. Pick the optimization first, the shape follows. That's the meta rule for the rest of the module, the one you'll come back to when none of the 4 obvious answers feel quite right.
Part 1. Parallel dispatch.
The fastest pattern when subtasks are truly independent.
The shape.
One orchestrator at the top, and workers below, each handling an independent subtask. The lines fan out. The orchestrator dispatches to all workers in a single message. What independent means here is precise. Each worker has everything it needs to do its job from its initial input. No worker waits for another to finish. No worker reads another worker's output mid-flight. No shared mutable state. They're independent because they could each run in a separate universe, and the result would be the same. The win is wall clock time. When you dispatch 4 workers in parallel, total elapsed time becomes the slowest worker plus a tiny bit of orchestration overhead, not the sum of all 4. So if each worker takes 30 seconds, parallel finishes in 30-something seconds, while sequential finishes in 2 minutes. The cost dimension matters too. 4 workers running in parallel cost the same in tokens as 4 running sequentially, but the user gets the answer 4 times faster. That's pure value, no trade-off, when the work is genuinely independent. The trick is recognizing when it actually is. The technique that turns dispatch into parallelism is one specific detail: multiple tool calls. Single message. When the orchestrator emits a message with 4 task tool calls, the runtime fires all 4 in parallel. The orchestrator then waits for all 4 to complete and gets all 4 results in one shot. That's parallel. If the orchestrator emits 4 messages, each with 1 task call, those run sequentially. The runtime waits for each message's tool calls to complete before processing the next. That's sequential. Same task calls, same agents, same prompts. But how you compose the assistant turns determines whether the work parallelizes. This is the single most important detail to internalize about parallel dispatch. The parallelism comes from how you compose the tool calls, not from a magic parallel flag somewhere in the API. If you're writing a / command or an orchestrator agent, lean on this. List the agents you want dispatched in the same paragraph of the prompt, with explicit in parallel language. The runtime knows what to do. For canonical use cases for parallel dispatch, they all share a shape. Research swarms. You have a question that benefits from pulling context from 5 sources: internal docs, external APIs, search results, codebase, prior conversations. 5 agents go in parallel. Synthesizer agent at the end pulls the threads together. Multi-perspective review. Same input, different lenses. Security review.
Performance review.
Test coverage review. Documentation review. Same code, for agents, for reports. We saw this in Module 3's /review. That was a parallel dispatch pattern with a synthesizer. Multi-region or multi-shard checks. Same query, different data shards. Each agent queries its assigned shard, returns results. Aggregator merges. A, I, B/C generation. 3 variants of a piece of copy. 3 different style approaches. 3 different angles on the same idea. User picks. The common thread. Independent subtasks producing comparable returns. No shared mutable state. If your subtask shares state, or if one needs another's output to start, parallel is the wrong pattern. Move on to sequential pipeline in a few slides. After your N workers return, what do you do with the N results? 2 strategies. Simple concat. Cheap, fast, low overhead. The orchestrator appends the 4 returns into one report. Maybe groups them by severity. Maybe deduplicates by key. Pure code, no extra LLM call. Use simple concat when each return is already structured, like 4 reviewer agents each returning a verdict plus issues object. The combining work is just merging. Synthesizer agent. Pricier, but earns its keep when the returns conflict or overlap. Failure handling matters more for parallel than people expect. With one agent, failure is binary, succeeded or didn't. With N parallel agents, you can have one of 4 fail, and the question becomes, what should the system do? 3 responses.
Degrade.
3 of 4 return successfully. Proceed with what you have. Mark the missing piece. Part 2. Sequential Pipeline. The right pattern when stages depend on each other. The shape. A horizontal pipeline. Each stage has a clear job. Data flows left to right. Plan decomposes the request into a spec. Build takes the spec and produces code. Review takes the spec and the code and produces a verdict. Ship takes an approved verdict and finalizes, commits, deploys, notifies, whatever your release flow looks like. The arrows aren't decorative. Each arrow represents a data contract. The spec flowing from plan to build is a real, structured object. The code flowing from build to review is a structured diff plus notes. The verdict flowing from review to ship is approve or changes required with specifics. When this pattern works, it works because each stage is small, focused, and has a clear input-output contract. When it fails because contracts got hand-wavy and stages started doing each other's jobs. The discipline of sequential pipeline is contract discipline. We'll spend the next 2 slides on that because it's where the leverage is. Each stage produces a structured return that the next stage parses. Plan returns a spec, goals, constraints, acceptance criteria. Build accepts the spec and returns a diff, a list of changed files, and self-review notes. Review accepts the spec and the diff and returns a verdict, approve or changes required, plus an issues list. Ship runs only if the verdict is approved. Why does it have to be this shaped? 3 reasons.
1.
The contracts make the pipeline testable. You can fixture each stage independently and assert the output shape. Now you have regression tests at every transition.
2.
Contracts make state persistence. 2 options for where the data between stages lives. State in prompts. Cheap and fast. The whole spec or whole diff lives in the prompt the next stage receives. Everything in context, nothing on disk. Best for short pipelines where the artifacts are small, say, a spec under 500 words, a diff under 200 lines. State in files. Persists across stages. Scale.
Part 1. Parallel dispatch.
The fastest pattern when subtasks are truly independent. A real example. The discuss, plan, execute, verify pipeline that's becoming a default for spec-driven coding agents.
Discuss.
Part 3.
Supervisor plus spécialiste.
The pattern when expertise depth matters more than parallelism. 3 routing strategies, in order of increasing cost. Description-based routing. Each specialist description tells the orchestrator what kind of request fits. The orchestrator picks based on phrasing match. This is what Claude Code's auto-routing already does. You've been using description-based routing every time the orchestrator picks a subagent for you. It's free. The orchestrator is doing the routing as part of its normal operation. Explicit rules. Why specialize at all? Why not one generalist agent that handles every language? For reasons. Domain depth wins. A Rust specialist with 800 words of Rust idioms and ownership rules in its system prompt outperforms a generalist 8 times out of 10 on Rust tasks. The same generalist trying to know Rust and Python and TypeScript and Go ends up shallow on all 4. Smaller contexts. Specialist design checklist. 5 things every specialist needs. Identity. 1 paragraph that names the domain explicitly. You are a senior Rust engineer specializing in async runtimes and lifetime correctness. Not your code helper. The narrowness is the point. Domain knowledge. Built into the system prompt directly, or loaded on demand via a skill. The Rust idioms, the testing patterns, the common gotchas. This is what the generalist couldn't carry. This is what makes the specialist a specialist. Hard constraints. Things this specialist refuses, even within its domain. The Rust specialist might refuse to suggest unsafe blocks without explicit user authorization. The TypeScript specialist might refuse to introduce new dependencies. Hard constraints. Scope the specialist's blast radius. Output contract. Same shape across siblings. Verdict, issues, summary. This matters because the supervisor needs to compare and combine specialist returns. If they all return different shapes, the supervisor's job becomes adapter work instead of routing work. Trigger phrasings. Distinct from sibling specialists. Zero overlap. If the Python specialist and the TypeScript specialist both trigger on the word function, your routing collapses. Real example. /debug. A supervisor pattern in action. The command body acts as the supervisor. It detects the language of whatever the user passed in Python, TypeScript, Rust, Go, and dispatches to the matching specialist. Each specialist debugs in its own domain, with its own deep knowledge of that language's failure modes. The Python debugger knows about PDB, knows about common Essentio gotchas, knows where to look for type-related runtime errors. The TypeScript debugger knows about source maps, knows about common React rendering issues, knows the difference between compile time and runtime errors. Same problem shape, debugging, different domain knowledge. The supervisor, that command body, does almost nothing. It detects the language. It dispatches. It structures the specialist's return for the user. One command, one supervisor for specialists. A real shape worth shipping. The pattern scales. When you need to add a fifth language, you add a fifth specialist and update the routing rules. The existing four don't need to change. That's the leverage. Part 4. Iterative refinement. The pattern when quality is hard to hit on the first try, but easy to evaluate. The shape. 2 nodes. Generator and critic. Generator produces a draft. Critic evaluates it. If the critic isn't satisfied, feedback flows back to the generator with specific notes. The generator produces a new draft incorporating the feedback. Critic evaluates again. The loop continues until convergence. Either the critic approves or you hit a stop condition. Why does this pattern work? Because for many tasks, evaluating quality is genuinely easier than hitting it on the first try. A critic can recognize this paragraph buries the lead without being able to write a great paragraph itself. A reviewer can spot a security vulnerability without being the one to fix it. The asymmetry is real, and iterative refinement exploits it. The catch is that loops can run forever. We'll spend the next 3 slides on the safeguards that make this pattern viable in production. Without those safeguards, iterative refinement is a footgun, a way to burn arbitrary amounts of compute without convergence. With them, it's one of the most powerful patterns in the toolkit. 4 convergence criteria. Wire at least 2 of them, always. Critic approves. The verdict comes back as approve. Ship the latest generator output. This is the happy path. Most loops should exit through here. Score threshold met. The critic returns a numeric score on each iteration. Once the score crosses above your threshold, you stop. Useful when approve is too binary and you want to be able to tune strictness via a single number. No change iteration. 2 consecutive drafts come back essentially identical. The generator has converged whether the critic agrees or not, diminishing returns. Stop and ship. Max iterations hit. Hard cap. 5 is the default I'd start with. When you hit the cap, halt and surface the latest draft along with the unresolved feedback. The user gets to decide whether to ship as is or escalate. A loop with only critic approves as a stop condition can run forever if the critic is too strict. Always wire at least 2 stop conditions. Most of mine wire all 4. Critic approves is the happy path. The other 3 catch the cases where the happy path doesn't hit. 3 explicit safeguards. Wire all 3. Belt, suspenders, second pair of suspenders.
Mux iteration cap.
Hard limit, default 5. When you hit the cap, the loop ends. Surface the latest output plus the unresolved feedback to the user. Don't pretend you converged. Be honest about hitting the cap.
Cost ceiling.
Halt if total token spend across the loop exceeds a budget. This is the safety against runaway cost. You set the budget per system ahead of time. The loop monitors actual spend after each iteration and bails if it crosses the line. Never let a runaway loop drain wallets. There are stories of teams running up four-figure surprise bills because their loop didn't have a cost gate. Quality plateau. If 3 consecutive drafts score within 5% of each other, stop. You've converged in practice even if the critic technically didn't approve. This is the safeguard against an over-strict critic that keeps demanding tweaks the generator can't make. All 3. The downside of having all 3 is one wasted run when one of them triggers a stop you didn't actually need. The downside of not having them is unbounded compute.
Pick the small downside.
Cost control inside the loop. 5 tactics that compound.
1.
Pass only the change sections after iteration 1, not the whole draft. The generator already wrote the rest. It doesn't need to rewrite what didn't change. Massive token savings.
2.
Use haiku for the critic. The critic's job, evaluate quality on a checklist, is well-scoped extraction.
Haiku does that fine.
Save opus or sonnet for the generator, where reasoning depth matters more.
3.
Cap critic feedback length. 3 issues max, prioritized by severity. The critic doesn't need to list every nit. It needs to surface what matters most. Capping the critic's output also caps the generator's next iteration input.
4.
Stop sooner. Most loops overiterate. Converge at acceptable, not perfect. The generator at iteration 5 is rarely meaningfully better than the generator at iteration 3. Usually it's just chasing tail-end critic preferences.
5.
Cache identical subtasks. If the generator regenerates the same paragraph twice, hash the input and reuse. This is overkill for most loops, but it's a technique to keep in your back pocket for high-volume systems. Iteration is cheap when bounded. Iteration is expensive when each cycle pays the full cost of the previous one. The tactics above are how you keep it bounded. Real example. A writing critic refining marketing copy. Generator drafts a 200-word marketing paragraph for a sales page. Critic scores it on 5 dimensions: clarity, hook, specificity, tone, length. If the aggregate score is below 4 out of 5, the critic returns 3 concrete revisions. Generator applies the revisions, returns the new draft. Repeat until score crosses 4 or 5 iterations elapse. In practice, most copy converges in 2 or 3 iterations. The first draft is rough. The generator hits clarity and length, but misses on hook. Round 2 fixes the hook, but introduces a tone. Live build, in pseudocode form. The orchestrator's loop. Initialize a draft from the generator using the spec. Loop up to 5 times. Each iteration, run the reviewer on the spec plus the current draft. If the reviewer's verdict is approve, break out of the loop. Otherwise, refine the draft using the reviewer's issues list. Check the cost guard if we've blown past the budget, also break. After the loop, return the final draft, the iteration count, and the final verdict. 8 lines of orchestration. The agents do all the substantive work. The orchestrator's job is just to wire the loop and protect against runaway. This is the last section.
Part 5.
Pattern selection. The framework that tells you which of the 4 shapes fits your problem. 3 axes determine the shape. Axis 1. Subtask shape. Are the pieces of work independent of each other or dependent on each other's outputs? If independent, parallel patterns are on the table. If dependent, you want a sequential or iterative pattern. Axis 2. Result quality. Is first shot good enough, or does the work need iteration to hit quality? If first shot is fine, parallel and supervisor are on the table. If iteration is needed, sequential pipeline or iterative refinement comes in. Axis 3. Domain expertise. Does the work fit a generalist, or does it want a specialist? If generalist, parallel, and sequential work. If specialized, supervisor is on the table. The mapping table on screen captures the canonical combinations. Independent plus first shot plus generalist.
Paralleldispatch.
Dependent plus iterated quality plus generalist. Sequential pipeline. Independent plus first shot plus specialized.
Supervisor plus spécialiste.
Dependent plus iterated plus same agent. Iterative refinement. The matrix doesn't replace judgment. It makes the judgment explicit. When you can place your problem on the three axes, the right pattern usually announces itself. When two patterns both fit, you've got a hybrid candidate, and we cover those next. Hybrids. Real systems usually combine two or more patterns. Sequential pipeline with a parallel stage. The outer shape is plan, build, review, ship, but the research step in the middle fans out to three sources in parallel. We saw this in the worked example a few slides back. Common shape for research-driven coding agents. Supervisor, where one specialist runs an iterative loop internally. The supervisor routes to the right specialist. That specialist happens to be a generator-critic loop optimizing its own output. From the supervisor's perspective, it's calling one specialist. From inside the specialist, it's iterative refinement. Parallel dispatch, where each worker is itself a small pipeline. Three workers in parallel, but each worker runs a tiny plan, build, verify cycle. Pattern smells. 5 signals that you picked the wrong shape. Cascading failures. One subtask fails, and the whole system collapses. That's a sign you treated dependent work as if it were independent, parallel, where you should have been sequential. The fix is to switch to a pipeline with explicit gates between stages. Idle agents. Most workers are waiting for one slow worker to finish. That means you have hidden sequential dependencies disguised as parallel, agents that look independent but actually need each other's output. The fix is to identify the dependencies and either serialize or restructure the subtasks. Redundant work. Multiple specialists keep solving the same subproblem. That's wrong axis. You've built a supervisor pattern when you should have built a sequential pipeline that does the shared subproblem once and hands the result downstream. Convergence miss. The iterative loop never satisfies the critic. 3 causes, criteria too strict, no plateau detection, or wrong pattern entirely. If after 3 iterations the score is barely moving, you've converged in practice even if the critic doesn't agree.
Routing fog.
The supervisor picks the wrong specialist half the time. That's almost always trigger overlap or weak descriptions. Tighten the trigger phrasings, make them disjoint. Routing accuracy will jump. Smells aren't fatal. They're signals to revisit your axis assignments. When something feels wrong, run back through the 3-axis matrix. You'll usually find the wrong axis call you made on the first pass. The architecture spec. The deliverable for this module. 1 page. 6 sections. Problem statement. 1 paragraph. The user request you're solving, in their words, plus what good looks like. Pattern choice. Which of the 4 or which hybrid combination, and a 1-line rationale. Sequential outer pipeline plus parallel research stage, because research subtasks are independent but downstream stages depend on consolidated findings. Agents and roles. List each agent. Its scope, its model, its tools. 1 line per agent. Data contracts. The shape of every handoff between agents. JSON-shaped, schema style. Not prose. Literal structure. Failure plan. Per agent, what happens on failure. Degrade, retry, abort. Spelled out, not improvised. Verification gates. What halts the system between stages. Contract validation, test runs, score thresholds, whatever's appropriate. 6 sections. 1 page. Hard constraint. The single-page rule is the discipline. It forces you to commit and prevents the spec from drifting into vague prose. The spec is the contract between you and your future self when you come back to debug this thing 6 months from now. Diagram conventions. 3 rules that keep the diagrams readable.
Nodes.
Each agent is a node. Color code by role, orchestrator in coral, workers in slate, critics in mint, specialists in gold or whichever palette you're using. The color is information. Consistent coloring lets you read a diagram at a glance and know which agent does what kind of work. Edges. Each handoff is an edge. Label it with a data contract, spec, diff, verdict, issues. Direction shows data flow. Don't draw bidirectional arrows unless you literally mean iteration. Bidirectional arrows confuse readers. Annotations. Use small text alongside the relevant edges to call out gates, retries, and iteration caps. Retry once on transient. Halt if verdict is changes required. Max 5 iterations. These annotations are where the failure plan from your spec becomes visible in the diagram. If you can draw it, you can build it. If you can't, you've got more design to do. The diagram is a real-time correctness check on your design. When you can't figure out where to put an arrow, that's a sign your contracts are vague or your roles are ambiguous. Fix the design. Redraw. Worked example. Watch how the conventions come together. Outer shape. Sequential pipeline. Plan, then research, then build, then review, then ship. 5 stages. Data flows left to right. Each arrow is labeled with what flows. The interesting part is the research stage. Internally, it's parallel, 3 sources running simultaneously. Archive. Internal docs. Web search. Each source returns its own structured findings. The research stage aggregates them before handing off to build. This is a hybrid.
Sequential ou tes pipelines plus parallèles in stage.
The shape captures the natural structure of the problem. Research benefits from parallelism, but build needs all the research consolidated before it can start, and review needs the build complete before it can run. When you draw your own systems, you'll find that almost all of them are hybrids of this kind. Pure parallel dispatch is rare in production. Pure sequential is rare. Pure iterative is rare. The combinations are the norm. The skill is recognizing which parts of your problem want which pattern, then composing them cleanly with clear contracts at every transition. The diagram is what makes that composition visible. The spec, fully written out. 12 lines that capture every choice. Problem: code change requires reading current literature first. Pattern: sequential pipeline plus parallel research stage, a hybrid. Agents: planner on Sonnet with read and grep. Researcher running 3 haiku agents in parallel pulling from Archive, Docs, and Web. Builder on Opus with read, edit, and write. Reviewer on Sonnet with read and bash. Contracts: spec flowing into research, research findings into diff, diff into verdict. Failure plan: research parallelism degrades on individual source failure, review failure loops back to builder. Gates: contract validation between every stage. 12 lines. Every choice articulated. Anyone reading this can either build the system or critique your choices and propose a better design. That's the bar. The spec doesn't say which prompts the agents use. It doesn't say which exact tools each agent calls in what order. Those details belong in the agent files themselves, not in the architecture spec. The spec is the contract. The implementation is downstream. If you can write this spec for your problem, you've designed a system. If you can't, the design isn't done yet, and that's useful information. Quick recap of what an hour of Module 4 has given you. You can now do 5 things. Recognize the 4 canonical orchestration patterns wherever they appear. Pick the right pattern for your problem using the 3-axis matrix. Compose hybrid patterns when one shape isn't enough. Diagram nodes, edges, and contracts cleanly. And write a 1-page architecture spec for any system you design. The assignment for Module 4. 1-page architecture diagram for a real problem in your work. 3 deliverables in the 1 page. Pattern choice with a 1-line rationale. Name the pattern and tell me why the other 3 are wrong for this problem. Agents, their roles, their contracts, the failure plan. All of it on a single page. No 2-page exceptions. If your diagram doesn't fit on 1 page, your design isn't done. The single-page constraint is the discipline. It forces you to compress to the essential and resist the urge to add more boxes when the design is unclear. The page: 3 concrete actions. 3 time horizons.
Today.
Pick a real problem in your work. Run it through the 3-axis matrix. Note which pattern wins and articulate why the other 3 are wrong. 30 minutes. Don't draw anything yet, just decide which shape fits. This week, draw the architecture diagram on one page. Nodes, edges, contracts. Use the conventions from slide 35. Get someone, a coworker, a friend, anyone with engineering taste to critique it. Their critique tells you where your design is hand-wavy. This month, build a prototype of the system you diagrammed. The diagram is the spec. Ship the system. You don't have to ship a polished version. A prototype that demonstrates the pattern with all the agents wired and the contracts honored is enough. The point is to take the design from the page to working code. If you can draw it, you can build it. Module 5 next, multi-agent system design. We'll take the patterns from this module and add the design discipline that keeps real systems from collapsing under load. See you there. Up next, Module 5, multi-agent system design. Where Module 4 was about choosing the right shape, Module 5 is about making the chosen shape actually work in production. 4 topics. State passing. Prompts versus files versus tool returns. When to use which. The trade-offs in real systems with real artifacts. Context isolation. Protecting the main agent from sub-agent context bleed. The discipline that prevents long-running systems from drifting into incoherence over time. Verification gates. Catching failures at handoffs before they cascade. Where to put the gates and what they should check. The 5 failure modes. Context bloat, role drift, cascading hallucination, agent loops, silent partial success. The actual failure modes you'll see in production, with one prevention pattern per failure. Module 5 takes the patterns from Module 4 and hardens them into systems that survive contact with real users, real workloads, and real edge cases. See you in Module 5. Bring the diagram you drew this week. We'll be hardening it into a real system, line by line.